Hi everyone. Today we're going to be talking about the water quality assessment that we did on the Chippewa River and at Lake Isabella. The purpose of the study was to assess the water quality at predetermined locations along the Chippewa River using various methods, including physical, chemical, and biological features. We also wanted to focus our project on the Lake Isabella impoundment and look at how it impacts water quality in the Chippewa River. The sites chosen for this study were predetermined by our professor, Dr. McNaught, at various points along the Chippewa River and at Lake Isabella. All of our data for our assessment was collected on April 10, 2021. Our first site of the day was along the Chippewa River at Rowland Road. The second was at Lake Isabella, and our third was along the Chippewa River at Coldwater Road. Our first site along the Chippewa River at Rowland Road was surrounded by mostly agriculture and forested areas, with the main vegetation being trees, grasses, and shrubs. As you can see, the Rowland Road site was located next to a bridge, but was also forested. Although not pictured here, there were many agricultural zones located nearby the site as well. The site also has natural vegetation growing in the riparian zone and was not well groomed, as you will notice in some of our other sites. The next site at Lake Isabella had mostly residential zones, but some forested and agricultural zones as well. Similar to the Rowland Road site, Lake Isabella had trees, grasses, and shrubs as the main vegetation. The Lake Isabella site is located next to a boat launch. In fact, people were launching their pontoons as we were at the site. When looking at these photos, you can see on the left that there is some forestry and woody vegetation. In addition, although you can't really see it, there are agricultural zones in the distance as well. You can also see some really nice lakefront properties on the lake as well. Nearby, we saw large houses that have boat docks, well-groomed lawns, and seawalls. You can even see in this photo how nicely the grass is kept. The last site along the Chippewa River at Coldwater Road was mainly residential and forested, and, like the other sites, had trees, shrubs, and grasses as the main vegetation. If you look at these photos, you can see that there is some forestry located upstream, but you can also see residential homes on the bank of the streams as well. Just like at the Lake Isabella site, you can see how well groomed the lawns are. There is not much natural vegetation in the riparian zone to reduce things like flooding and sedimentation. In our water quality assessment, we were most interested to see how the water quality measurements changed from the Rowland Road and Coldwater Road sites on the Chippewa River, because the Coldwater Road site labeled here as Site 3 was located downstream from an impoundment that was built to create Lake Isabella.
To collect the physical measurements at each site that we visited, we fully submerged a YSI multi-parameter probe into the water, which can detect many properties of water, but we were only interested in temperature, dissolved oxygen, pH, and the specific conductivity. And we also used field kits to find the alkalinity, which is just a measure of the number of basic compounds in the water, and hardness, which is a measure of metallic ions like calcium that are dissolved in water. The final physical test that we performed at each site was a Secchi disc reading, which uses a simple Secchi tube which has a small white and black disc at the bottom, and you slowly raise it until you can see it, and then you drop it again until it disappears. And the average of the depth of disappearance and reappearance is the Secchi depth. To measure the discharge of the river at the inlet and the outlet, we used a flexible tape measure to first get a full width of the river. And once we had that full width, which was roughly 15 meters at each site, we split that width into equal segments to get multiple readings of velocity and depth across the river. We used a simple measuring stick to record depth, and we used a Marsh-McBurney velocity meter to record the velocity of the water. Unfortunately, the water level at the outlet was far too high for us to collect velocity and depth measurements across the entire width of the river, so we were only able to get a few readings. But nonetheless, once we collected the data, we did some simple calculations in Excel, which included multiplying the width of each segment by the depth, which gives area, and then multiplying that product by velocity to get a discharge value in meters cubed per second.
We measured the concentrations of nitrate and phosphate at the 3 different sites using Hach testing kits. In order to do so, we followed the instructions for each kit to get the measurements. In addition to testing for nitrate and phosphate levels at each site using the Hach kits, we also collected water samples in 1-liter bottles to have the concentrations measured using instruments from Dr. Uzarski's lab. To get a better understanding of the health of the stream, we used D-nets in order to capture and count macroinvertebrates on the river bottom. We made sure to sample different parts of the river to get different types of invertebrates that we could be used in order to determine the overall health of the river. Once we chose our spots, we faced downriver while having the opening of the net facing upriver. Once the net was placed on the ground, we shuffled our feet in order to kick up rocks and any other debris on the bottom that could be holding the different organisms. After we shuffled our feet for about a minute, we looked inside of the net to make sure that we had some organisms for us to count on shore. We then placed the macroinvertebrates into enamel-colored bins for counting. To aid in counting and identification sheets were used with pictures in order to get an accurate count for the amount of macroinvertebrates found at our river sites.
These are the results of the temperature, dissolved oxygen, and Secchi readings that we collected at each of the sites we visited. The temperature and dissolved oxygen at the inlet were 13 degrees Celsius and around 10 milligrams per liter, respectively, which were the lowest readings of the 3 sites that we visited. At Lake Isabella, we recorded the highest readings of temperature and dissolved oxygen, which were roughly 14.75 degrees Celsius and 12 milligrams per liter, respectively. At the outlet, the temperature was roughly 14.25 degrees Celsius and the dissolved oxygen was roughly 11 milligrams per liter. In terms of Secchi depth, both the inlet and the outlet had roughly the same clarity of water. Using the Secchi tube was not an exact measurement, however, because the tube maxes out at 120 centimeters, which in both samples the disk was visible at the bottom of the tube. Nonetheless, Lake Isabella had the lowest Secchi depth of roughly 81 centimeters. All these sites are well suited for photosynthetic organisms because there was relatively little cover and a lot of sunlight available.
For the physical measurements, temperature, Lake Isabella impoundment could be increasing the temperature of the lake and the outlet. It's likely very shallow, and the lake is so small that it's not even considered a lake by most sources. And then for oxygen, there is a lot of activity on the lake. This could account for the increase of oxygen in the Lake Isabella site. The impoundment outlet could be incorporating a lot of oxygen into the system as well, which could account for the increase in oxygen outside of the lake on the outlet. For the Secchi depth, both the inlet and the outlet had the max Secchi depth, but Lake Isabella had a lower depth. While collecting at the Lake Isabella site, a boat launched at the nearby boat launch, so this could account for the increase in turbidity. For canopy cover, all 3 sites are open. The 2 rivers are fairly residential. This is likely contributed to the lack of canopy cover despite the river being fairly narrow.
At the inlet, the highest discharge rate that we recorded was 0.675 cubic meters per second, which was the highest near the middle of the river at 9 meters from shore. Interestingly, the deepest portion of the river at 12 meters from shore had less discharge despite the larger cross-sectional area of flow. The total discharge for the inlet was 2.12 cubic meters per second. Like I mentioned earlier, the data was difficult to collect at the outlet due to the water level being too high, but even with us only collecting only 4 meters from shore, the total discharge rate at the outlet was much higher at a value of 4.38 cubic meters per second. So despite the cross-sectional area of flow being much smaller, at the 4-meter segment, the discharge rate was so much higher because the water was moving significantly faster at this leg of the Chippewa River. We suspect that this is due to the dam, which is not far upstream. From our discharge results, it's obvious that the discharge at the outlet was much greater than the discharge at the inlet, which we suspect is due to the impoundment, which is not far upstream. Although the video doesn't play, you get a good picture of the water moving quickly over the impoundment. Since there does not seem to be much structure within the middle of the river to dissipate the energy gained by the water as it goes over the impoundment, the water carries the energy further downstream. The higher velocity water has multiple impacts for the downstream ecosystems as well. First off, certain species may not be able to live in higher velocity streams because they do not have a way to stabilize themselves against the current. Some species, like the flattened body mayflies, have flattened bodies to reduce drag against the current. Black flies, which produce a glue-like substance to stick themselves to structures at the river bottom, and other species that have claws or bury themselves in the sediment are adapted to high currents, but other species may not be. The result is somewhat of a fragmented habitat for the species that are incapable of resisting the high currents. Not only are macroinvertebrates threatened, but the soil of the river and the banks are more likely to be eroded due to higher discharge rates as well. A higher sediment load impacts all life in the river, like fish who may be suffocated by sediments entering their gills, and even plants whose access to sunlight may be limited due to suspended particles. The sediment load does not seem to be significantly higher as of now at the outlet due to our Secchi depth readings being the same at the inlet. These impacts are certainly still possible in the future.
Now for the chemical results. The pH did not vary too much between the three different sites. The Rowland Road site, which was our inlet, tested at a 7.57 pH. Lake Isabella tested as an 8.06 pH, while the Coldwater Road tested at an 8.130 pH. Compared to other rivers in Michigan, specifically the Clinton River in Sterling Heights, measured at an 8.1 pH as of May 2nd, 2021 at 11 a.m. Eastern Standard Time. This was found using a website called waterdata.usgs.gov/Michigan. The conductivity at the Rowland Road site, which was again our inlet, measured at a 321, while Lake Isabella was measured at 296, and the Coldwater Road site, which again was our outlet, was measured at 295. Compared to some other rivers that have been posted on waterdata.usgs.gov, these values were really low, which I was kind of surprised about. The alkalinity for the Rowland Road site, which again was our inlet, was measured at a 170 milligrams per liter, while Lake Isabella was measured at 153 milligrams per liter. Test kits were used, kind of like the Hach testing kits, were used to measure both the alkalinity and the hardness for the three different sites, but due to time constraints, the alkalinity was not measured at the Coldwater Road site. The hardness for the water at the Rowland Road site and at Lake Isabella both measured at around 221 milligrams per liter for the water hardness. The Coldwater Road site measured at 255 milligrams per liter with the water hardness kit.
For chemical measurements, pH, there wasn't much of an increase in pH between the three sites. The pH that all the sites were at is a great level for fisheries. Conductivity, it decreased at Lake Isabella and Coldwater River, so not much metal is being added due to the impoundment. Alkalinity, again, there's not much change between Rowland Road and Lake Isabella. The alkalinity is at a good level for fisheries, and alkalinity was not measured at Coldwater Road site. Hardness, the fast-flowing water coming out of the outlet could be eroding the bottom and the sides of the river. Mount Pleasant's water is naturally harder water. This is due to soil, so it is likely that the riverbed has a fair amount of calcium and magnesium that created the increase in hardness.
This nutrient data was collected from the water samples that were sent to Dr. Uzarski's lab that we collected. The total phosphorus for the Rowland Road site was measured at a 0.029 ppm. The Lake Isabella site tested at a 0.022 ppm, while the Coldwater Road site measured at a 0.019 ppm. When converting the parts per million to micrograms per liter, we found that the total phosphorus levels indicated that Lake Isabella is mesotropic, based just on the total phosphorus in the water that was tested. The nitrate level at the Rowland Road site was measured at a 0.534 ppm, while the Lake Isabella site measured at a 0.109 ppm, and the Coldwater site was 0.112 ppm. In order to more correctly identify if Lake Isabella was oligotrophic, mesotrophic, or eutrophic, more testing would have to be done. A Secchi depth test would have to be completed, as well as a chlorophyll type A test, which tests for the amount of algae found in the lake. Once both those tests have been completed, a better determination can be made about the condition of Lake Isabella itself.
For nutrients, there is higher nutrients at the Roland Road site and lower nutrients at Isabella and the Coldwater site. We found zebra mussels at Coldwater Road, and since Lake Isabella is frequently used for boating, it is likely that zebra mussels were introduced into the lake and traveled downstream. This could be an explanation for the lower nutrients since they take up phosphorus. As far as nutrients go, the Lake Association wants a really healthy lake. While we were collecting the samples at Lake Isabella, one of the residents who lives on the lake came by and said that if there's anything that needs fixing, let them know and they'll fix it. And he seemed pretty serious on making sure that they had a really healthy lake system.
At the Roland Road site, we collected 96 organisms from 14 different species. The site had a total IBI score of 45, which indicates a river with good water quality. At the second site, we collected 27 organisms from a total of 8 species. After the IBI calculations were done, we came up with a score of 20, which indicates a river with fair quality. Here's a graph showing the different macroinvertebrates collected at each site. As you can see, we collected many more organisms at the Roland Road site than at the Coldwater Road site. At both sites, the 2 species that were found the most were naked caddisflies and scuds. At Roland Road, we also collected a lot of stonefly nymphs and mayfly larvae as well. I wanted to note that at the Coldwater Road site, we also found invasive zebra mussels, which means that they have invaded the Chippewa River and most likely have made significant impacts on it. We do see a relatively large change in the IBI score between the sites. The Roland Road site has good water quality and the Coldwater Road site has fair water quality, indicating that there is a decrease in water quality as you go down the river. This change in water quality could be due to the impoundment located just upstream of the Coldwater Road site. Based on our data, the dam likely has an impact on how fast the water is flowing, which could limit what sort of organisms can live there, as they must be tolerant of high speeds. Another explanation for a lower IBI score may be because we were unable to collect in all parts of the stream at the Coldwater Road site because of how fast the water was moving. In addition, we spent much less time collecting macroinvertebrates at the Coldwater Road site than at the Roland Road site because we had to get back to campus. We only collected 27 organisms at the Coldwater Road site, which may be a reason why the Coldwater Road site only had fair water quality and the Roland Road site had good.
As far as management, the water coming out of the impoundment at Lake Isabella is moving very fast. It is likely causing erosion and not allowing organisms to inhabit this area because of the fast-moving water. There are several ways to manage this issue. The first is deflectors. This is the cheapest and easiest way to manage this problem and involves putting up deflectors along the river to slow down the water and reintroduce the pool-riffle sequence. The second is the run-of-the-river dams. This is much more costly and involves removing the impoundment and replacing it with a dam that allows the rivers to flow more naturally downstream. These type of dams include check dams, wedge dams, a barrage, and weirs. Another issue is to help minimize sedimentation and runoff. There is very little vegetation in the riparian zone to protect the river and lakes from sedimentation and runoff. The ways you could help is by adding grasses and sedges along the edge and allowing for natural vegetation to grow. You can also reduce the use of fertilizers on lawns. Many of the lawns in the area of all 3 sites were kept really well and were likely fertilized regularly. In conclusion, we had some strange data points that are likely errors that we definitely were not expecting. Some reasons for these errors were we were a small group, there was just 4 of us, and we had to work very fast to collect all of the data that we needed. There could be human error as well while running the tests, not taking enough time while doing them, not taking enough measurements, or even collecting macroinvertebrates, collecting them unevenly. We collected macroinvertebrates for a lot longer at the Roland Road site than we did at Coldwater Road site. In the future, a way to make this project a little bit more reliable is you could take multiple measurements to get an average so that you have more of a view of what the river looks like over time. And to do timed searches for the macroinvertebrates, the same time for each site, and make sure that you cover every part of the river.